In this lecture, we will review two basic techniques, integration by parts and substitution, in evaluating definite integrals, especially with an eye to probability. Let's start with an example. Suppose we wanted to integrate from 0 to infinity t times e to the minus t. Well, there's no immediate antiderivative, but if we pretended for a moment that we had an antiderivative and it was t times minus e to the minus t, then we take the derivative of that and we should get the function we wanted back. But if we do take the derivative of that and we use the product rule, we get minus e to the minus t plus what we wanted, t times e to the minus t. So we have this added term. We could then correct for this added term. And that's what we do when we are using integration by parts. In a way, it's going to be undoing the product rule, and it's more of an art form than the product rule. All right, so continuing with this idea. So the integral from 0 to infinity of t e to the minus t is then the integral from 0 to infinity of d by dt of t times minus e to the minus t. And that part we know. And the fundamental theorem of calculus part 2 says that that integral and the derivative undo each other. And so we can just evaluate what we're differentiating inside at infinity and negatively at 0. But then we have this leftover term, which we integrate from 0 to infinity of e to the minus t. But we know that too. That has a known antiderivative, which is just minus e to the minus t. So we can again evaluate that at positive infinity and at 0. So we substitute in infinity in t times minus e to the minus t. Now here again, it's important to remember these improper integrals are limits. So it'd be like the limit as m goes to infinity. And if you substituted it m times minus e to the minus m, and then let m go to infinity, that goes to 0, because the e to the minus m goes to 0 much faster than the m goes to infinity. So that would evaluate to 0. And of course, substituting 0 in negatively, we would get 0 times minus e to the minus 0. So that's just 0 times 1, which is 0. Then for the other term, minus e to the minus t, you substitute infinity in and you get 0, and you substitute 0 in and you get 1. And so you'd wind up with minus e to the 0, which is just 1. So this is very typical of integration by parts, so we can write down the formula we used. So we don't have to go rethink this out all the time. So if we're looking at an integral of u dv, we can write that down now in indefinite integration form as uv minus the integral of v du. This is what I remember. So this is the only thing I remember about integration by parts. It's all you really need to know. Now, if we used a little different notation and wrote it out in the definite integral form, we'd have the integral from a to b of f g prime dx is equal to fg, evaluated positively at b and negatively at a, then minus the integral from a to b of f prime times g. So on the left, you have f times g prime, and on the right, you have f prime times g. The prime has moved over. But then we have to evaluate f and g at b and minus at a. And we have a negative sign in the integral on the right-hand side. Let's take another example. Suppose we wanted to integrate 0 to 2 pi of x times cos x dx. All right, so we want to apply this formula now. So what we could think of is that x, well, that's the u. And then the dv, that is cos x dx. Now we chose that dv because we know the integral of cos x is sine. And so v really is sine x. Now we can just apply the formula, so we could just write out uv, which is x sine x, evaluate that positively at the upper limit, which is 2 pi, and negatively at the lower one. But in both cases, sine is 0, and so we're just going to get 0. And then we subtract off the other part, which is v du. Well, v we figured out is sine x, and u is x, so du is just dx. So we subtract off the integral from 0 to 2 pi of sine x. Well, the integral of minus sine x is cos. The value of cos at 0, you get 1, but then you subtract off cos at 2 pi, which is also 1, so that's 0.
So we're adding 0 to 0, and we'll wind up with 0.
The other common trick to simplify integration is substitution, which corresponds to undoing the chain rule. Just like above we're undoing the product rule, now we're kind of undoing the chain rule. So for example, if we had to integrate from a to b of f of g of x times g prime of x, then that could be evaluated as the integral from g of a up to g of b of fu du. So what we really do is we let u equal gx and du equal g prime x dx, which just comes from the prior assignment. Let's take an example. So suppose we wanted to integrate from 0 to infinity t times lambda times e to the minus lambda t. Lambda is greater than 0, so this integral will make sense. It's an improper integral, and the reason why it makes sense is if lambda is greater than 0, e to the minus lambda t heads to 0 fast enough that this integration, the area under that curve, will be a finite number. Okay, we'd like to simplify this. One common trick is to multiply and divide by lambda here. And so instead of dt, we're going to work with lambda dt. And that might seem slightly mysterious now, but there's always this manipulation step that we go through when we're using substitution or even integration by parts to try to get it in the right form. So we have now lambda dt at the end. We leave the middle part the same, lambda t e to the minus lambda t. And then we have to use linearity of the integral to pull a 1 over lambda out in front here. And so we're left with this equation here. And now it looks like we have something we could use, because we had in our head when we were doing this manipulation that we really want to let u equal to lambda t. So if we do that and let u equal to lambda t, then the integrand really is u e to the minus u, and the lambda dt at the end is just du. And so now we use this substitution and we evaluate this at g of 0. So you substitute 0 in and you get u is equal to lambda times 0, which is 0, and then up to g of infinity. If you substitute t as infinity in, you get infinity times lambda, which is still infinity. And now the integrand is u times e to the minus u, and that's what we integrate. Now, don't forget about the 1 over lambda we had to factor out to make the integration substitution work out. And finally, we know by the example prior to the previous one that this integral is 1. And so finally, we're left with just the 1 over lambda. Let's take one more example. Suppose we wanted to integrate from 0 to pi over 4 of sine x over cos x, which of course is just tan x. Well, we can do a little bit of manipulation. So if we're thinking our function f is 1 over, and our g of x, which is u, is going to be cos x, then we need to have a du. And so we almost have it because we have sine x, but the derivative of cos x is minus sine x. And so we need to multiply by minus 1 squared, and so we can manipulate this sine x into minus sine x dx. So there we have the du, and then out in front we have a u to the minus 1 because we just brought that denominator cos x out and then took the reciprocal of it, and hence we get the u to the minus 1. And then we have the minus 1 out in front because we brought another minus 1 in. And we're set to use substitution. So we evaluate the lower one, recalling that g here is cos. So at cos of 0, well, cos of 0 is 1. And then at the upper limit, it's going to be cos of pi over 4. Well, that's root 2 over 2. And then we're evaluating that with u to the minus 1 du. Well, at this point, you could note that 1 is greater than root 2 over 2, so you could use a property to interchange the limits of the integral, and multiply by minus 1. So you could write this root 2 over 2 up to 1 of u to the minus 1. Let's say we didn't do that. Instead, we just go ahead with this integral. That's also fine. The antiderivative of 1 over u is just ln u, because the derivative of ln u is 1 over u. And so what we're left with by the fundamental theorem of calculus is that we're evaluating minus times ln u positively at root 2 over 2 and negatively at 1. So we get minus ln of root 2 over 2 minus ln of 1, but ln of 1 is 0. So we just have minus ln of root 2 over 2, and that is just 1 over root 2. So we can then bring the square root out. By log properties, that square root then just multiplies out to become 1/2 out in front. So we're left with minus 1/2 ln of 1/2. But minus ln of 1/2 is just equal to ln 2. So we're left in the end with 1/2 times ln 2. So just in summary, we have re-exposed two of the standard techniques for evaluating integrals, that being integration by parts and substitution. And we've used this with improper integrals, and we've also done it in a few examples, which are sort of typical as you would encounter in applications such as probability. Thank you.